Welcome to our lecture on basic data structures. So the reason that we're going to talk about this today is we want to go over some of the basic built-in data structures that are provided by languages and that you should kind of use as your first tool to attack problems, any programming problem. Now, often a key part of solving a programming problem is just recognizing what data structure or data structures are the right ones to use. And once you have the right data structure, everything after that is relatively simple to do. So sometimes just knowing what that data structure is pretty much all there is to it. We're going to focus mainly on C++ examples here. And I'm going to focus on the things that are kind of built in that hopefully you're already familiar with all of the concepts that are here. And the key is just how would you make use of these and what are some of the considerations in terms of using them in programming. And we're going to skip over some of the things like graphs and some of the data structures that aren't built in, and we'll get to those in future weeks and talk about how you can use those. But mainly here, I want to talk about some of the standard stuff in C++. Realize that a lot of this, there are equivalents in other languages. So just because I'm giving C++ examples doesn't mean that you can't do the same things in Python or Java or something else. So the first thing to remember are that there are a variety of data types that are available to us. So most of these, you should at least be familiar with the idea, even though I would say the standard things from this list that people use are the bool, the int, the double, and the string, or maybe the float and the string. But realize that there actually are a lot of variations. So booleans for boolean variables, char, keep in mind that a char or char, depending on how you learned it, is really just an 8-bit integer. So even though it is an integer that's interpreted as a character, an ASCII character that gets output, what it actually is just an integer. And that means that you can do things like subtract one character from another and get an integer out as the result. So there are integers, there's short ints, long ints. We talked last time about how sometimes you need the long int, which generally is going to be 64 bits as opposed to a regular int that's generally 32 bits. And sometimes you need that in order to hold a sum or hold the product of two numbers. And also keep in mind that there's unsigned versions of integers. And so an unsigned version will generally double the upper end of what is available at the cost of not being able to represent negative numbers. Now there's also variation in floating point numbers, so besides the float and the double, you'll sometimes have long double, which can provide more precision than a double provides if that's supported. One thing to keep in mind is that your floating point operations are often a little bit slower than integer operations. Typically they are, and especially the long double might not be supported in hardware the same way that other things are, and so it might be particularly less efficient than say, a double would be. Then there's always a string class that's provided to you in something like Python. This is built into the language itself. In C++, you actually need to pound include string, but it's basically there for you to do operations with, and you should definitely be familiar with that. Now, one thing, I'm not going to go into it all here, but one thing to remember about string operations is that several of them don't work quite as efficiently as you might first think. So one thing that I've seen people already in our class run into trouble with is that, for instance, in Python, if you try to append a single character onto a string, it has to copy the entire string first. So the string it's not variable length where it can just extend. It actually creates a new string with a larger size. It copies the old one and then copies the character on at the end. And there's reasons for that in Python because of its flexibility in allowing you to basically add two strings together easily. That's part of how it's implemented, but it makes things slower than you might think otherwise. So if you keep appending stuff onto a string, character by character, that can take a very, very long time. Whereas I believe the string class in C++ is implemented like the vector, and it's easy to append one character on at a time. Now, here are some of the main data structures, and I'm going to go through all of these. We'll talk about them in a little bit more detail, but I just wanted to kind of put them all out here so that you could get a sense of some of the built-in data structures that it's helpful to be familiar with and be able to use in your programs. And as we go forward, I'll kind of assume that when these are available, you can make use of them. And so it's everything from kind of your standard stacks and queues to things that you might be a little bit less familiar with, like the unordered map or an unordered set. Again, I'm going to go through all of these. These examples that I show here, they're instantiated with integers everywhere, but in reality, instead of integers, those can usually be, I won't say any data type. Sometimes it has to be something that basically hashes, but you can have a wide variety of data types that are there besides integers that are within the template. Okay, so the arrays or vectors or lists are one of the most standard ways of storing data. Very often in the types of problems we deal with, we have to read in a bunch of data and process it, and so it's extremely common. In fact, I'd say probably in a majority of problems, you end up having to read in an array or list of data at some point and do something with it. Now, if your only consideration is speed, then usually using a static array, so this is just where you declare an array, and in fact I'll go back a slide so you can see it. This is just where you declare an array directly. That is usually the fastest thing to type, and it is actually slightly faster than vectors to be able to use, but it's less flexible. You have to know the size at that time. So if you know the size, that can sometimes be faster. When you are using the vector class, which is what I would usually recommend you use, I think the vector class is really nicely implemented. It's very efficient overall. For the most part, you're not going to notice the efficiency differences with arrays. And so generally, I would recommend using it. A couple of things to be aware of. One, if you use the square brackets to access an element, that is usually going to be faster than using the .at member function, because the .at is going to actually do error bounds checking and checks to see if something is within bounds or not. The square brackets don't, and so that means the square brackets are less safe than .at would be, but they're as a result they're also faster. Now the list is a linked list implementation, so I'll just say, if you remember back to when you learned about linked lists, there's some really good things about them. It becomes very easy to insert, and it's very easy to delete. Super efficient at doing that. It's much more efficient than doing that with a vector or an array, unless you're adding or deleting from the very end, from the very last position of a vector or array. But if you're trying to do anything in the middle, a list is very efficient for doing that. The only problem is it doesn't support things like sorting that arrays and vectors do, because you can't just index directly into the middle of a linked list. You have to use pointers to go through and follow. And in C++, you would use iterators to do that. So if you end up having something where you're doing a lot of insertion or deletion and you don't need to have this sort of random access into the middle of the list, then sometimes the list is a good way of handling your data. I would say that in my experience, the majority of the time, the vector is the thing that I want to use. Now, assuming you have an array or a vector, the common things that people want to do with them are sort them and search them. So those are kind of obviously things that you'd want to sort and search. If you are wanting to do a sort, very rarely is it worth the time to write your own sorting routine. It's only unless you really know that you need to optimize it in some particular way, or you need to have, some particular aspect of the sort would you ever write your own sorting routine. You might as well use built-in sorts that are built into C++. Now, I will say sometimes you do need a different comparison function, so you might want to change what makes one thing bigger or smaller than another, and this is especially true if you have a class or a structure trying to figure out whether one element of the class is greater than or less than another one. You might have to write a unique comparison function, but you don't have to actually rewrite the sort routine. So I'll talk about that in a minute. But the basic way that sort works is you call sort. You have to pound include algorithm, by the way. The algorithm is the library that you would use. And then you can just write sort and the beginning point of the vector or array and the end point of the vector or array. So if it's a vector, you would write a.begin and a.end. So a.begin is an iterator that points at the very beginning of your vector. A.end is an iterator that points just after the end. And similarly, for a static array, where you've just got a hard-coded array, you can just do A, which is the starting point of the array. It's the array name, but that's the index of the starting point. And A plus n is n elements later. So if the array is of size n, A plus n is the element just after the end of the array. And so that shows you where the end is. So you can just sort by that one command. Now, in C++, if you have an unsorted array, there is a way of doing a find operation without having to write it yourself. It's basically a search operation. I believe this also works for linked lists in addition to vectors and arrays. And what you get back is a pointer or an iterator to the array element. So you're not getting an index. You're not getting like an integer value. Instead, you're getting an iterator. And you can use the iterator to actually get the index if you need to. But it is the iterator. And so you have to dereference it to find the thing it's pointing to. So for a vector, that is called find. So again, you give the beginning and the end of the vector, or for the static array, the beginning and ending of the array, and then the thing that you're looking for. And it will return to you the iterator that points at that item. And if it doesn't find it, it will point to the end of the array. So it'll point to a.end or a plus n. Now, this is a key thing. If you have a sorted array, if you guarantee yourself and you say my array is sorted or my vector is sorted, then you can use a binary search. And obviously binary search is order log n instead of order n, and that's a huge difference. So pretty much anytime you can take something order n and reduce it to order log n, you save a tremendous amount of time. And so typically, this is what you would want to do. Most cases where you actually need to search, you would first sort, and then you would do a binary search on it. That tends to be the more common way to go. And again, C++ has a built-in binary search routine, and that's called lower bound. So notice it's not called search. It's not, and in fact, there's something called binary search, but binary search just returns a true-false value saying whether or not something is in there. It doesn't actually tell you where it is. You can't actually look at it. It just says, does it exist? And it uses a binary search to do that. The thing that you want to use is called lower bound. And so if you call lower bound, again, with the beginning and then one past the end of the vector or array, and the thing you're looking for, what you get back is an iterator that points either at that array element or the thing right after. Okay, so it's the first element that's not less than x. So if I have an array and it's got the numbers 1, 3, 5, 7, 9. It's got the odd numbers, and I'm looking for the element 8. Well, guess what? It's not going to be in there. Okay, but if I call lower bound, it's going to be pointing at the 9. Because that's the next thing that's not smaller than 8. If 8 was in there, it would be pointing at the 8. Okay? So that's true for a vector or for a static array. So again, you get an iterator back. You have to dereference the iterator and see what it's pointing to. There's also an upper bound. And so one thing about lower bound is you can use it to check to see if something is there. So you don't have to use binary search. You might as well use lower bound. And you just see, is the thing it ends up pointing to, like in the example I gave, is it 8 or is it something bigger than 8? Because if it's not 8, then it didn't find whatever was there. Right? It means it didn't find it at all. Now there's also something upper bound, and so that's going to give a pointer to the first element greater than x, but notice you can't use that to find x. So you're not finding something that's greater than or equal to x, it's the first thing greater than x. So you can use a combination of lower and upper bound sometimes to get ranges of things, but the point is lower bound is kind of your friend. That's the standard That's the standard binary search that most people are looking for. Now, a lot of times when you're doing a sort or you're wanting to sort things, you don't always want to sort from smallest to largest in terms of just a single value. So it's not always just a single value that gets sorted smallest to largest. Often you want to sort in some other way. And to do this, you might need to define your own comparison function. So I'm going to give an example of some of these on the next slide, but there's a few different ways to do that. So you can write a comparison process that returns a Boolean, and you can either write it as an operator or as a comparison function. Or there's I think some other options that are there. Those are the ones I tend to use the most. But the idea is they take two of the same element and they compare them, and you return something that's true if the first parameter is less than the second one. And not less than or equal, but less than. So if you're comparing A and B, you return true if A is less than B, and you return false otherwise. And so when sorts are done, it uses the sorting routines will use that comparison operation. So it's just another parameter. It's an optional parameter that you can add on when you call sort up here. So instead of sort a.begin, a.end, you would write sort a.begin, a.end, comma, and then whatever the comparison function you have. Unless A is a class, or sorry, the types in A are a class, and you've defined the less than operator. Okay, so it's going to use that to compare two different things, regardless of the sort algorithm that's there. Now, one thing that I'll mention is stable sorts, which, if you don't remember, a stable sort is something where if two things are equal, it leaves the order between them unchanged. And you have to, not all sorts are stable. So if you actually want to guarantee that you have a stable sort, instead of calling sort, you would want to call stable sort, where like CMP is your comparison function in this particular case. Okay, so to look at some of the ways that these things can be defined. So one operation is that, or one way of doing this is you can define a less than operator. That's the first example that you see up there. So you have something that is your left-hand side and your right-hand side of the less than operator, and it should return true if the left-hand side is less than the right-hand side and false otherwise. And so that gives you just a less than operator, and after that you can use that to compare two of that function to each other. Okay, you can also define a function, and that's like you see here, and I'll just say for me, this is typically the way I do it, although occasionally I'll define the operator. You can define a function, and it takes in two constant references to the things that you want to compare. And so, for instance, if you want to sort instead of smallest to largest, you want to sort largest to smallest, you can define a comparison that when it takes in the left-hand side and the right-hand side, it flips it around. It returns whether it's greater than or not. Okay, so that'll flip the whole comparison around the other way. And that's something that you pass in as that third parameter. Notice if you define the less than operator, you don't necessarily need to define a comparison operator or a comparison function. Okay, and so the other option is there's something called a functor. There's people who really like functors. I don't particularly like it myself, but that's just a personal preference. But it's basically an operator that you can define. You see the format there, and it'll return whether something is less than or the other one. And you can use a functor like the CMP function. Okay, so anytime that you need to do comparisons, this can be useful. I'll say one of the places it comes up a lot are priority queues, where you're trying to take the thing with the highest priority, and often you use one number for priority and then there's a bunch of data associated with it, and so you often will have to define something like a comparison function to decide what thing is really the highest priority among all the different options. And so whether you're doing a sort or a priority queue, or you're doing lower bound, or any of these things, you can use this to specify how things are compared when two things need to be compared. If you want the default behavior, you can use the operator for that. Okay. Now, let me talk for a minute about pairs and tuples. So pairs are a built-in way within C++ of pairing up two different elements. And there are other ways of doing this. The standard way would be you'd create your own class or struct, and you would just create the struct that has two of that type, and you could access the two elements of that type, and that's real easy to do. It's not actually that much code, but normally you have to define the struct ahead of time, and you have to name it, and then you have to use it, and so on. And sometimes it's just a little bit easier to use a pair. And I'll say some of the built-in STL algorithms that need to return two things, they will sometimes return a pair as the way that they return stuff. So sometimes you need to know how a pair gets used. But a pair is templated, and it takes in two different types. And once you have that, it's basically these two types paired together. So you might have an integer and a string. Okay, and so then for each integer there would be one string, like there would be an integer string pair that those two things go together. Okay, you could have two integers, you could have two strings. It can be a pair of two of anything. And if you ever want to create a pair out of nothing, you can always use the make pair command, and that will actually create a pair of the two different things. And then to access the two elements, the first thing is always whatever dot first, and the second thing is always whatever dot second. So if I had something like make pair 1, 3, and then I assigned it to p, if I wrote p dot first, that would be 1, and p dot second would be 3. Okay. There's also, sometimes you need more than two things. You need 3 or 4 or 5. And so C++ has a way, it started in C++ 11, a tuple that lets you group 3 or more elements together. And I'll just say personally, I find the tuple so clunky to use, I almost never actually use it, but the functionality is there. So occasionally I've felt like, okay, this is the cleanest way to do something. But the way it works is you define a tuple. It's, again, a templated class just like all the others, so you give all the different types of things that you want. So you do have to specify the type of each part of the tuple. And then you can call make tuple just like you did make pair, except instead of just 2 elements, you have n elements, however many n is. Now the problem here is you don't have nice things like first and second defined like you did for a pair. Instead, you have to get the first element, the second element, the third element, the fourth element, and so on. And so there is a templated function called get that is used to access the elements. And so if you see the code that's here on the screen, you have to write something like get, and then in angle brackets 0, and then in parentheses the thing that you want, the tuple that you want to get it from, and that will get the 0th element, the first element from the tuple. And to get the next element, the second one, you would do get angle bracket 1, and then in parentheses the tuple. And if you ask me, that's just like, that's really ugly and painful to write. And so that's one of the reasons I hardly ever use the tuple, but it's there. And so you can always store data in a tuple and get data out of a tuple that way. Now, one of the really nice things about pairs and about tuples is that the comparison between them is somewhat automatic. So if you compare two pairs, what it's going to do is it's going to first compare the first thing, and if the first things are equal, then it compares the second thing. Okay, and so having a pair is a simple way of creating a structure and automatically allowing comparison of the two things in the structure without having to write your own comparison function. So often, like, if I need something that's, just a pair of integers, I can create a pair of integers, and then I can sort that pair of integers, and it will sort it based on the first integer in the pair and then based on the second integer in the pair. And the alternative to that would be to create a structure that has, int a and int b, and then you have to create a comparison operator for that structure so that well, first I'm going to compare a's, and then I'm going to compare b's, and you'd have to write all of that yourself. That's a lot of writing, whereas otherwise you can just write pair int, and that's it. So pairs are real helpful, especially when you're doing competitive programming and you're interested in doing something fast. But I'd also say it's a pretty clean way of doing things. The downside is it's not very descriptive in terms of names. So when you write your own structure, you can give all the elements their own name and you can refer to them. It's a little bit cleaner in that sense, whereas here you just have first and second, and you have to remember what the pair is trying to describe and what the first thing is and what the second thing is. Okay, so the next data structures that we can talk about are stacks, queues, and decks, which the deck or the doubly ended queue is kind of a combination of a stack and a queue. And these work just like the standard stack and queue that you've always heard of. Remember that you can instantiate them with basically any data type so that you can push and pop stuff off of a stack and push and take the front off of any queue. And so each of them has their own things that they're good for. Queues are obviously great for processing things in order when you don't have a nice loop and you need to like bring stuff in and handle it later. Stacks are great when you are trying to simulate something like a function call, or they're also very good if you're trying to do matching. So you sort of push stuff onto the stack. Say you're trying to match up parentheses. You can push one set of parentheses on and then, you pop it off when you find closing parentheses and so on, and you can make sure that you have the right size stack in that case. Stacks are also a great way of doing reverse order when you don't have a simple loop. And in both of these, it's basically the same set of commands. The only thing that you have to remember is in a stack you use top and in a queue you use front. But both of them have push to put something new into them. They both have a size command that'll tell you how large it is, and they both have an empty command that'll tell you whether or not the thing is empty or not. Now there's also the deck, and the deck is a doubly ended queue, so you can push and pop from both the front and the back, and so you have push front, push back, pop front, and pop back. And you still have things like size and empty. And you also, kind of just like with the queue, you have front and you have back that you can just look at the thing in the back. And notice that just because you are calling something like top or front or back on any of these things, that's not actually popping it off. That's just telling you what that thing is that's on there. So once you're ready to remove it, you have to actually pop it off. Deck also has the square bracket operator, so you can directly index into a deck. Now, I'll mention that for the most part, there's actually not that many things out there that you actually need a deck for. It's a real interesting data structure, but most of the time what you actually want is a stack or a queue or something like it. If you might want something more like a vector. So it's actually pretty rare that you need something like a deck. There are, you can come up with a very few cases where deck is just the right thing that you need to use, but more often than not, either a stack or a queue or a vector is going to do everything that you want it to. One thing to keep in mind is when we get to graphs, when you're doing depth first search, you'll use a stack, and breadth first search, you'll use a queue. So we're going to see these things come up over and over in the future as we do other types of problems as well. Now, another data structure, and one that you might have learned when you took 221, you learned the heap data structure, and the way that that's implemented is as a priority queue. So the C++ structure is called the priority queue, but what's actually implemented underneath is a heap. Now, one thing that is not implemented, and this is actually kind of annoying, is there's nothing about changing the key for a heap. So you can't actually access anything in the heap except the thing that's on top. And so if you want some of the other heap operations that you might have learned about, things like, increase priority or any of that, you need to actually implement your own priority queue separately. So you can't use the built-in priority queue to do access into the heap structure itself, even though what it's actually using is a heap. But as long as the thing that you care about is just you need to pull off the biggest thing, and by the way, you can implement a priority queue with a different comparison function if you want to. So if you don't, it's always going to be the quote biggest, but you can define what biggest means. You can use the built-in priority queue function. And so the basic operations that you have are push to put something into it, top to see the thing that's on top, and pop to remove the thing on top. And then you can check whether it's empty or not. And priority queues, they get used for things like shortest path algorithm and minimum spanning tree. So again, when we get to graphs later on, this is going to come up again. If you have greedy algorithms, when we get to greedy algorithms, we're going to use priority queues to prioritize the next thing to do. And so it's a way of getting this information without actually having to enter everything and doing a sort or repeatedly sorting. If you keep calling sorts over and over, that can often be too slow. This is a much simpler way to do it. And I will mention that when you couple this with with a pair or a tuple, if I have a pair, I can make the type 1 thing the thing that I want to sort on, and type 2 the thing that I'm actually wanting to sort. So if I have a lot of data or I have things, and each of those things has some priority, well, I can put them in a pair where the first element of the pair is the priority and the second element of the pair is everything else. And that way I can run my priority queue and it will always pull out the highest priority item. And I'll mention that if you ever, like another simple hack is if you're trying to get something and you want the lowest priority, so you want the lowest number instead of the highest, you can just enter the negative of everything and pull it out and use the priority queue. You just have to remember that you're always pushing in negative values, and then you have to negate things when you pull them out at the end. Okay, so there's also the set structure. So sets or unordered sets are a way of just keeping track of distinct elements. Now a set is still ordered, kind of obviously by the fact that we don't write unordered underscore in front of it. And that's actually usually implemented as a binary search tree underneath, whereas an unordered set is generally implemented as a hash table underneath. And so you've learned from 221 about the differences between hash tables and binary search trees. There's reasons that you'd want each one, but basically if you need to have something where stuff is in order, where it's actually in a sorted order, then you want to use set. If you don't care about the order, you just need to know if it's there or not, then you can use an unordered set. Typically what I would say with that is if you ever need to like do more advanced set operations than whether something is in or out, use set. And if you just need to keep track of whether you have things or not, like have I encountered this, yes or no, use an unordered set. That's sort of just a rule of thumb that you need. Now, there are some C++ algorithms, so if you use the algorithms library, you get some algorithms that work with sets, and that lets you do set union, set intersection, set difference, and set symmetric difference. And actually, I'll point out that any sorted range, so this can be a vector or it can be a list or whatever, but if it's a sorted range, you can use these algorithms. It doesn't have to be the set that does them. These are algorithms that apply anytime you have an iterator where you give it the beginning and ending iterator and everything in between is sorted. It'll do union, intersection difference, or symmetric difference. Now, there's one other way that you can handle a set, and I'm going to mention this here, although it's not a built-in structure by any means, and that is if you have really small sets of items, so things that are like no bigger than 32 or 64 is typical, and sometimes you can get super long integers that go up to 128, 128-bit integers, then you can basically use the integer representation in binary form to keep track of whether the elements of the set are there or not. And so the idea is you represent your set as a single integer, and the bit indicates whether that item is in the set or not. So if the 0th bit is set, the ones digit, if that element is set, then it says, in other words, if it's 1, it means that thing is in the set. If it's 0, it means it's not in the set. And so you can do things like do a union between two things by doing a bitwise OR. So that's just a single vertical bar. So a single vertical bar does a bitwise OR. It does an OR between two things, but it goes bit by bit instead of just is the overall value true or false. And remember, true is anything non-zero, false is 0. But a bitwise OR is going to be something that does it one bit at a time. And so you can create a set. So like say that I have a set of 3 numbers, 5, 17, and 8, and I can create an integer out of that, and I can add the 5th bit, the 17th bit, and the 8th bit. And to set an individual bit, one way of doing that is you take the number 1 and you shift it over a certain number of shifts. So 1 shifted 5 over, that's the double arrow to the left. That's a bitwise shift of the 1 over 5, binary digits. Same thing with 17 and 8. Okay, so for instance, my set of 5, 17, and 8, I can just do a bitwise OR, the union of the set containing 5, the set containing 17, and the set containing 8. You can also do an intersection with a bitwise and then you can also do an XOR if you want to between two things by using the up arrow, the little exponent looking caret. I didn't actually put this on the screen here, but you can do exclusive OR between two things in that case. If you want to get something that's all of the elements, that has every single one of them, then if you take 1 shifted n to the left and then subtract 1 from there, if you think about it, that's going to be all the different elements, and by subtracting off 1, you have 1 fewer element than you would have otherwise. You can also do the complement, so that if you get everything that is like everything that's not in the set, so if you've got n elements and you want everything but n, the way to do that is you do a bitwise AND with the 1's complement. And the 1's complement, you use the tilde in front of x, and then again you use the all elements. So basically you do the bitwise AND between those two things. And the reason you have the bitwise AND with the all element things is to make sure that you're removing any high-level things beyond n. So if you only have an n, if the maximum number of elements you have is n, and remember you're usually limited to n being like 64 or something. If that's the case, then you can use this to remove any of those high-level bits. To see if an element I is in the set, you just take x, where x is your set, and you do a bitwise AND with 1 shifted I to the right. That's basically the set containing just I. And so you can see, does the set containing I, is that in X? Well, if the bitwise AND is non-zero, then it's in the set. Okay, so this is just a quick set representation. If you hopefully you find this interesting. There's a whole lot of bitwise manipulations we can do, and I'll try to talk about some of those in class time in addition to this, but just realize that you can use an integer to represent a set by using the individual bits of the set, and then all of your operations become relatively simple and extremely fast operations that you can do on those sets. Okay, so kind of I believe the final topic that I want to talk about are maps, or unordered maps. And this is where you have your key value pair, and it's the way you often learn about hash tables. So what is usually done underneath is, again, either a binary search tree or a hash table, depending on whether it's an ordered map or an unordered map. An unordered map is going to be faster to use, but you won't be able to have any ordering between the elements, so they're not in any type of order between them. So generally, unless you have large keys where hashing can take a long time to do a comparison, or if you need an ordering, then generally the unordered is better. But there are times that you want to use just a regular old map. And so the basic idea is, once you've defined a map, so like this is a map, this example that you see at the bottom is I'm defining a map named M, and it's going to be indexed by a string, and then it's going to have an int value. Okay, so string is the index, int is the thing that will be stored. And so in this case, then, once I have that, I can write things like m of the string this equals 5. So I'm assigning 5 to the element that's hashed by this. And this is a good way, it's especially useful in dynamic programming if you want to like store data that you've seen before, or store things you've computed before, is you can store something related to some key. You can store whatever the value of that thing is using a map or an unordered map. And you can look it up later. Now, I will mention that there is that a key thing here is that if the key doesn't exist and you put it in the brackets, it's going to create it, like the process of checking it is there. So you should use the find command if you actually want to see, does a particular element exist or not. Okay, rather than just doing that. Okay, so the last thing related to that is there's also a multi-set or a multi-map, and these are versions of the set or map that let you have multiple entries. And so if you're going to have like multiple things that have the same key, or you're going to have a set where the same element can be repeated multiple times in the set, you can use the multi-map or the multi-set. And again, there's unordered multi-set and unordered multi-map, just like before. If you want to count how many elements have a particular key, you can use the .count command. And the problem with all of these is you don't have the bracket or the @ operators because there's not just a single value anymore. So you can't just say like, what is the value for this particular key, because there could be lots of values. And instead there's an operator called equal range, and that's going to give you a set of iterators that you can use to go through, and it'll tell you all the things that match that particular key. So if I have a multi-map and I give it a key and I entered 5 things with that key value, it'll give me a list of those things, of all of those elements that had that particular key, where my starting iterator points to the first one and my ending iterator points just after the last one, so that you can just do a loop just like you would any other loop. Okay, so that's a relatively quick overview. During class time, I'm planning to go over examples of a lot of these things, but I wanted to at least introduce these topics. If these are not things you're familiar with, I would really recommend you try programming through some of them yourself. Try them out. See if you can use some of these structures, see if you can create your own versions of all of these and implement them. I'll say for the next problem set in our class, I'll be expecting you to use some of these data structures on those problem sets because it makes it much easier to solve them, and I'm just expecting you'll do that rather than implement them on your own. And remember, make use of whatever is provided for you in the library, so there's no sense in reinventing the wheel if it's already available.